Okay, so I'm going to take you through the Year 9 summer assessment. We'll go through each question in turn, telling you the answers as we go, and then a little bit about each question as we go through. So if you've got your paper to hand, probably a periodic table as well, and then a pen. Obviously you can pause and rewind as need be. But obviously, if we start with question 1, this one's about changes of state. Fairly standard diagram here. We've got the words. You could obviously have seen the solid liquid gas diagrams before actually drawing the particles, etc. But this was actually just giving you the words this time. So it's asking you in the first question, which arrow represents evaporation? So evaporation is obviously from a liquid to a gas. So for this one, we can easily identify arrow P. So obviously arrow P is already identified as the answer for the first question. Second one, asking us which one is melting. So melting is obviously solid to liquid. So that is going to be arrow R in this example. And then obviously while we're here, S would be freezing or solidifying, and Q would have been condensation. Would that have been the question? So going back to question 2, R was the answer for melting. So just 2 questions on that one. But then went into a cooling curve question. Again, fairly standard, done this as an experiment in the labs. But what we've got is, first question, what processes occur in between points B and C? So obviously this is where we've got the horizontal line. So we know that there's probably some sort of change of state occurring here. It started at about 96, 97 degrees, it's cooling down and it's undergoing a change of state between B and C. Now there is probably some information in the question, here it is. It's saying that at point A this is a liquid, so as the liquid cools down, that change of state will be liquid into solid. So that will be freezing at that point. So it's changing state. So obviously it could have been condensation or freezing, depending on the state it was at A. But obviously freezing being the answer to this one. And the temperature remains constant between those temperatures because it's undergoing a change of state. The substance isn't being heated because it's cooling down. There could be some sort of thermostatic water bath going on, but for the fact that the temperature changes over a different period of time, it all stays constant for a certain amount of time, means it'd probably not be the second answer, I should say. Bonds being formed is the correct answer. Bonds being formed releases energy. That substance would ordinarily have wanted to cool down. However, that cooling down is compensated by the bonds which are being made, or the bonds which are being strengthened from a liquid to a solid, giving out energy, allowing it to essentially remain at a higher temperature than it would have ordinarily. And obviously, because it's cooling down, it's not evaporating. So it's not the last answer either. Okay, so if we go to the last question in this one then, that's not the answer, just click that. But why does the temperature become constant again at point E? So obviously we've gone from a liquid, changed state, and then we've gone down to a solid. But you can see this temperature here is starting to remain constant again. Now it's just below 30 degrees, may cool down another couple of degrees, 27, 28 degrees perhaps, but fundamentally the point of this is that the substance is now at room temperature. Okay, so obviously it's not in a fridge, it's just on a lab bench or wherever you're doing the experiment, and it's just getting to the temperature of the room. So if you put it in the fridge, it cool down, if you heat it up, it go back up, but ultimately there'll become some equilibration between the temperature of the room, not necessarily the chemical process generating that temperature. It's literally just cooled down. That's the temperature of the room, just below 30 degrees, so a relatively warm room. Room temperature generally appreciated to be 25 degrees C. So into question 3. This is a solubility curve, perhaps a different curve to the type that you may have generated in the lab yourself. And also there would have been a second line potentially drawn on here at some stage. But sodium sulfate, it's got different temperatures, different amounts of solubility for the various temperatures from the experiment. And in the first question, we've said at what temperature is the solubility of sodium sulfate the greatest. So they're wanting to know the temperature at the greatest solubility. So obviously solubility is on the y-axis, so it's the highest point up. The highest point is this one here. So what we need to do is read off the temperature from the x-axis, and that's coming out at something around 35 degrees. Okay, that's the highest point on the graph. Read off the x-axis. And so now we've got to actually use the graph here, and what we've got to do is estimate the maximum mass of sodium sulfate that can dissolve in 100 grams of water at 20 degrees. So this becomes important later on, but first of all, just check that the amount of water we're using is the same amount of water we're using in the graph. So in this situation it is. And what we have to do is estimate the mass of sodium sulfate that's going to dissolve at 20 degrees. So find 20 degrees on the x-axis, read off the point, okay, and then read off to the y value here, and extrapolate the value off. You're going to get a number in the region of 26 grams by just reading those points off. So moving on, if we have a saturated solution containing 36 grams of sodium sulfate, what temperature is the solution at this time? So this is just going to ask us to go the other way around. So we've got 36 grams, again, in 100 grams of water. Just make sure that's right. It's different in a later question. So 36 grams. So if we read off 36 grams on here, so 36 is going to be here, that's this point here. Again, reading down to record the value, something in the region of 25 degrees. Just using those values. So, and then we go to the question where we did change the value here. We changed this to 50 grams of water. A couple of things we need to be aware of here. So what we've got is 25 degree solution cooled to 20 degrees. Okay, so we've got to take those two values. So we've got 25 degrees, which is this one here. Now we've already seen this one in the previous question. Assuming we got this right. This was 36 grams. So remember the 36 grams. We also had to then go to 20 degrees, sorry. And at 20 degrees, we had 26 grams. So we're actually using these two values here within the previous question, actually. It helps to make the maths a little bit easier in the fact that we're not confusing the question, but in another exam they can ask you different values. But we've got 36 grams of substance cooling down to 26 grams of substance which can dissolve. That means that surplus 10 grams of solid will recrystallize from the solution as a solid. You can filter that off, etc. But remember, this is in 100 grams of water. So if we had 10 grams of solid recrystallizing for every 100 grams of water, if we only had 50 grams of water, we're going to generate half of the 10 grams, and that's only going to leave us with 5. Okay, so there'll be 5 grams for that. Okay, so carrying on. Question 4. This is now going into some sort of periodic table type question, and what we've got is a generic outline of the modern periodic table, obviously with no real elements, just random elements, just given letters. And the first question is asking us which element has got 7 electrons in its outer shell. So fairly standard question about group chemistry. In order to have 7 electrons in its outer shell, it's going to have to be in group 7. So numbering from left to right, group 1 to group 2. We then jump the middle block to group 3, 4, 5, 6, 7. And so anything in this vertical group here will have 7 electrons in its outer shell, and group 7 will be over here. So for this one, that's going to be Q, because remember, groups give you information about the number of outer electrons of a substance. Likewise, the horizontal ones, as opposed to being groups, these are the periods, and so anything in period 3 is going to be on the 3rd row down. Okay, but what we must always remember is that what we appear to be the first row is actually the second row. There is this smaller row of hydrogen and helium on a fully labelled periodic table, but we've got that top row there being period 1, period 2, and then period 3 here, and as you can see there's only L within period 3. Question C though asks us which is a transition element. Transition element is basically the group in the middle. This is the, group, probably the incorrect term there, but this is the block of elements which don't have a group assigned to them. These are just the transition metal elements. They're sandwiched between official group 2 and group 3 here. Transition